In the heart of our galaxy, a star races around a black hole at a fraction of light speed, and in the time-lapse of its 16-year journey, we see time itself bend each orbit, revealing how gravity warps spacetime, turning the black hole's shadow into a cosmic clock. This star, S301, hurtles through the void at 3% the speed of light, its path a tight spiral around Sagittarius A*, the supermassive black hole at our galaxy's core. What we witness isn't just motion, but a dance between gravity and relativity. The star's light stretches and slows as it nears the event horizon, creating a flicker of time's distortion. For a moment, we're not just observing the universe, we're glimpsing the rules that govern it, written in the arc of a star's orbit. In the heart of our galaxy, a star named S301 is dancing around a supermassive black hole, and its journey has revealed a profound truth about the nature of time and gravity. This time-lapse, captured over years of observation, shows how the star's orbit around Sagittarius A*, the black hole at our galaxy's center, has provided direct evidence for Albert Einstein's theory of general relativity. For decades, scientists have studied this region, but the movement of S301 has offered a unique glimpse into how gravity warps space and time, confirming predictions made over a century ago. Let's explore how this star's dance has rewritten our understanding of the universe. At the core of our Milky Way lies a black hole with the mass of about 4 million suns, compressed into a region smaller than our solar system. This immense gravity has long fascinated astronomers, but observing its effects on nearby objects has been challenging. Stars orbiting this black hole move at incredible speeds, and their paths are influenced by forces we can only fully grasp through Einstein's equations. S301, a star with a mass similar to our Sun, is one such object. Its orbit around Sagittarius A* is elliptical, bringing it as close as 120 astronomical units, roughly the distance between the Sun and Pluto, at its closest approach. This proximity means the star experiences extreme gravitational forces, making it an ideal laboratory for testing the limits of general relativity. The time-lapse of S301's orbit was created by combining thousands of images taken over several years. These observations, conducted using advanced telescopes like the Very Large Telescope in Chile, allowed astronomers to track the star's motion with unprecedented precision. What they found was astonishing. The star's path wasn't just influenced by the black hole's gravity, it was also affected by the curvature of spacetime itself. According to Einstein's theory, massive objects like black holes bend the fabric of space, causing nearby objects to follow curved paths. S301's orbit, however, showed deviations that couldn't be explained by Newtonian physics alone. These deviations, known as relativistic effects, confirm that gravity isn't just a force but a distortion of spacetime. One of the most striking discoveries was how the star's light was stretched and shifted as it moved through the warped spacetime around the black hole. This phenomenon, called gravitational redshift, occurs when light climbs out of a gravitational well, losing energy and shifting toward the red end of the spectrum. By measuring these shifts, scientists could determine how much the black hole's gravity influenced the star's motion. Additionally, the star's orbit revealed a subtle precession, a wobble in its path caused by the black hole's immense mass. This effect, predicted by Einstein's equations, is similar to how Mercury's orbit wobbles around the Sun, but on a much larger scale. These observations provided direct confirmation of general relativity's predictions, even in the extreme conditions near a supermassive black hole. The significance of S301's orbit extends beyond confirming Einstein's theory. It also offers insights into the dynamics of the galactic center, a region where stars, gas, and dark matter interact in complex ways. The black hole's gravitational influence shapes the orbits of nearby stars, and studying these orbits helps scientists map the distribution of mass in the galactic core. S301's path, for instance, suggests that the black hole's gravity is stronger than previously thought, which could refine our understanding of how supermassive black holes affect their host galaxies. Moreover, the star's extreme environment provides a natural laboratory for testing the limits of general relativity, a theory that has withstood countless experiments but has never been tested in such an extreme setting. The observations of S301 were made possible by cutting-edge technology and international collaboration. Telescopes like the Very Large Telescope, equipped with adaptive optics systems, allowed astronomers to capture high-resolution images of the galactic center despite the vast distances involved. Adaptive optics compensates for the blurring effects of Earth's atmosphere, enabling precise tracking of the star's motion. These observations required years of data collection, with each image contributing to a growing picture of the star's orbit. The team behind the study, including researchers from institutions around the world, worked tirelessly to analyze the data, ensuring that every detail was accounted for. Their efforts highlight the power of modern astronomy to probe the universe's most extreme environments. What makes S301's orbit so remarkable is that it allows scientists to observe the consequences of general relativity in real time. Unlike the famous case of Mercury's orbit, which requires decades of observation to detect its precession, S301's motion is visible within a human timescale. This makes it an ideal candidate for studying how spacetime curvature affects orbital mechanics. The star's journey also raises intriguing questions about the nature of black holes and their role in galaxy evolution. For example, how do supermassive black holes influence the formation and distribution of stars in their vicinity? How do their gravitational fields interact with dark matter and other unseen components of the galaxy? These questions remain at the forefront of astrophysical research, and S301's orbit provides a crucial piece of the puzzle. Beyond its scientific implications, the study of S301 underscores the enduring power of Einstein's theory. General relativity, formulated in 1915, has withstood every test it has faced, from the bending of starlight during solar eclipses to the precise timing of GPS satellites. Yet, the extreme conditions near a black hole push the theory to its limits, offering a unique opportunity to explore its validity in the most extreme environments. The observations of S301's orbit not only confirm Einstein's predictions but also inspire new questions about the nature of gravity, spacetime, and the fundamental laws that govern the universe. They remind us that even in the most hostile regions of space, the principles of physics remain as robust as ever. As we continue to study stars like S301, we are not just confirming the past, we are laying the groundwork for the future of astrophysics. The techniques developed to track this star's motion will likely be applied to other objects in the galactic center, potentially revealing more surprises about the black hole's behavior. Moreover, these observations could inform our understanding of black holes in other galaxies, helping us piece together the role these cosmic giants play in shaping the universe. The journey of S301 is a testament to human curiosity and the relentless pursuit of knowledge, reminding us that even in the darkest corners of space, there is always more to discover. The journey to capture the time-lapse of star S301 orbiting the supermassive black hole at the galaxy's center began with a combination of cutting-edge technology, decades of observational patience, and a deep understanding of how gravity shapes the universe. At the heart of this discovery was the need to track a star moving at extraordinary speeds, over 3% the speed of light, while remaining within the intense gravitational pull of Sagittarius A*, the black hole at our galaxy's core. This required instruments capable of resolving details on an astronomical scale, instruments that could peer through cosmic dust, measure minuscule shifts in position, and capture changes over years. The tools used were not just telescopes, but networks of telescopes, each contributing a piece of the puzzle to reveal the dance of light and gravity in the galaxy's most extreme environment. The first step in this process was the identification of S301 itself. In the early 2000s, astronomers using ground-based telescopes like the European Southern Observatory's ESO, Very Large Telescope, VLT, began systematically mapping stars near SGR-A star. These stars, known as S-stars, orbit the black hole at incredibly close distances, making them ideal candidates for testing Einstein's theory of general relativity. S301, discovered in the early 2000s, stood out not just for its proximity to the black hole but for its unusually tight orbit, completing a full revolution around SGR-A* in just a few years. This made it a prime target for long-term observation, as its motion would be highly sensitive to the black hole's gravitational influence. But tracking such a star required more than just powerful telescopes. The challenge lay in the immense distance between Earth and the galactic center, which is over 27,000 light-years away. At that distance, even the slightest shift in a star's position on the order of a fraction of a milliarc would be nearly impossible to detect without advanced instrumentation. To overcome this, astronomers turned to a technique called interferometry, which combines light from multiple telescopes to create a virtual telescope with a much larger aperture. The VLT's gravity instrument, developed as part of the European Southern Observatory's ESO, became a key player in this effort. Gravity uses a network of 4 VLT telescopes to combine their light into a single, ultra-high-resolution image, allowing scientists to measure the position of S301 with unprecedented precision. Gravity's capabilities were further enhanced by its ability to detect minute changes in the star's motion over time. By observing S301 repeatedly, astronomers could track its trajectory around SGRA* and measure how its velocity changed as it approached and receded from the black hole. These observations were critical for testing predictions from general relativity, which posits that the black hole's gravity should cause the star's orbit to precess, essentially, to wobble in a way that's distinct from the simple elliptical paths predicted by Newtonian physics. The data collected by gravity provided the first direct evidence of this relativistic effect, confirming that the black hole's immense gravity warps spacetime in ways that align with Einstein's equations. However, gravity was not the only instrument involved in this groundbreaking work. The NASA/ESA Hubble Space Telescope also played a vital role, offering a complementary perspective on S301's motion. Hubble's high-resolution imaging allowed scientists to track the star's position over decades, providing a long-term record of its orbit. Unlike ground-based telescopes, Hubble's location above Earth's atmosphere eliminated the blurring effects of atmospheric turbulence, enabling measurements that were both precise and consistent. By combining Hubble's data with gravity's high-resolution observations, researchers could cross-check their findings and build a more complete picture of S301's path around the black hole. The timeline of this research spans several decades, with the initial observations of S301 beginning in the early 2000s. Over the years, as technology advanced, the accuracy of these measurements improved dramatically. By the 2010s, gravity had become operational, and its data began to reveal subtle deviations in S301's orbit that could only be explained by the black hole's gravitational field. These findings were further refined in the 2020s, as astronomers refined their models of the galactic center and accounted for additional factors, such as the distribution of dark matter in the region. The culmination of this work was the creation of a time-lapse that not only showed S301's orbit but also demonstrated how its motion was influenced by the black hole's gravity in ways that align with Einstein's theory of relativity. The process of capturing this time-lapse was as much about patience as it was about technology. Each observation required meticulous planning, as the stars near SGRA* are faint and their positions are difficult to measure with the required precision. Astronomers had to account for the Earth's movement around the Sun, the rotation of the galaxy, and even the subtle effects of cosmic dust that could obscure their view. To mitigate these challenges, they used advanced software to analyze the data, adjusting for these variables and isolating the true motion of S301. This level of precision was essential, as even the smallest error could lead to incorrect conclusions about the black hole's properties or the validity of general relativity. One of the most remarkable aspects of this research was the collaboration between different observatories and institutions. The ESO, NASA, and other space agencies worked together to pool their resources, sharing data and expertise to achieve a common goal. This collaboration extended beyond the instruments themselves. It also involved the development of new analytical techniques and the refinement of existing ones. For example, the use of adaptive optics technology that allows ground-based telescopes to compensate for atmospheric distortion was critical in improving the clarity of observations. These efforts reflected a broader trend in modern astronomy, where large-scale collaborations and interdisciplinary approaches are becoming increasingly necessary to tackle complex scientific questions. The significance of this work extends far beyond the study of a single star. By observing S301's orbit, scientists have gained insights into the nature of supermassive black holes and their role in shaping the structure of galaxies. The data collected also provides a unique opportunity to test the limits of general relativity in extreme conditions, where the predictions of Einstein's theory are most rigorously challenged. In doing so, this research contributes to our understanding of fundamental physics and the behavior of spacetime in the presence of immense gravitational forces. The time-lapse of S301 is not just a visual representation of its motion, it is a testament to the power of human ingenuity and the relentless pursuit of knowledge in the face of cosmic challenges. As the final pieces of the puzzle came together, the time-lapse of S301 became a vivid illustration of the interplay between gravity and motion in the galaxy's most extreme environment. It showed the star's journey around SGRA* in a way that was both beautiful and scientifically profound, capturing the essence of a phenomenon that has captivated astronomers for decades. The process of discovering and confirming this motion was a journey of perseverance, innovation, and collaboration, highlighting the incredible capabilities of modern astronomy. Through the combined efforts of advanced instruments, meticulous observation, and theoretical insight, scientists have brought us one step closer to understanding the mysteries of the universe and the role of black holes in shaping it. The star S301, observed in a time-lapse near the supermassive black hole at the Milky Way's center, offers a unique window into the extreme physics of spacetime. This isn't just about watching a star orbit a black hole, it's about testing the limits of our understanding of gravity, relativity, and the structure of the universe itself. At the heart of this phenomenon lies the interplay between massive objects and the fabric of spacetime, a relationship that has been the subject of scientific inquiry for centuries. When we observe S301's motion, we're not just tracking a star's path, we're probing the very nature of gravity as described by Einstein's theory of general relativity. This theory predicts that massive objects like black holes warp spacetime, creating gravitational wells so deep that even light cannot escape them. The star's orbit, however, provides a way to study these effects indirectly. By measuring how S30,000 years of motion reveal the black hole's gravitational influence, scientists can infer properties like its mass and spin, parameters that are critical for understanding how supermassive black holes shape their surroundings. Yet, the significance of this observation extends beyond the black hole itself. The galactic center, where S301 resides, is a region of intense activity, with stars, gas, and magnetic fields interacting in ways that challenge our models of astrophysical processes. Studying S301's orbit helps us unravel how these forces balance each other, offering clues about the dynamics of star formation, the behavior of matter under extreme conditions, and the role of black holes in galactic evolution. The time-lapse data also serves as a testbed for our theoretical frameworks. For decades, scientists have debated how gravity behaves in the presence of supermassive black holes, particularly in regions where spacetime curvature is extreme. Observations of stars like S301 provide empirical evidence to refine these models, ensuring they align with the real-world behavior of celestial objects. Moreover, the study of such systems is vital for understanding the broader implications of black holes in the universe. Supermassive black holes are found at the centers of most galaxies, and their influence extends far beyond their immediate vicinity. By analyzing how stars like S301 respond to their gravitational pull, we gain insights into how these cosmic giants regulate star formation, fuel accretion disks, and emit powerful jets of energy. These processes, in turn, shape the evolution of entire galaxies. The significance of S301's orbit also lies in its role as a natural laboratory for extreme physics. Unlike laboratory experiments, which can only replicate conditions on a limited scale, astronomical observations allow us to study phenomena that occur under conditions impossible to recreate on Earth. The black hole at the Milky Way's center, for example, has a mass millions of times that of the Sun, creating a gravitational field so intense that it distorts spacetime in ways that challenge our classical intuitions. By observing how S301 moves through this environment, scientists can test predictions about how gravity behaves in such extreme conditions. This includes phenomena like gravitational time dilation, where time runs slower in stronger gravitational fields, and the bending of light around massive objects, a prediction of general relativity that has been confirmed through observations of distant stars and galaxies. The time-lapse data from S301's orbit provides a real-world example of these effects, offering a unique opportunity to validate theoretical models. However, the study of S301 is not without challenges. The galactic center is shrouded in dense clouds of interstellar dust, which obscure visible light and make direct observations difficult. This is why astronomers rely on infrared and radio telescopes, which can penetrate the dust to reveal the hidden dynamics of the region. Instruments like the Very Large Telescope Interferometer (VLTI) have been instrumental in capturing the precise movements of stars like S301, allowing scientists to track their orbits with remarkable accuracy. These observations require years of data collection, as the star's motion is slow on human timescales but dramatic over cosmic timespans. The patience and ingenuity of astronomers are evident in the way they piece together these observations, using advanced technology to overcome the limitations imposed by distance and intervening matter. The significance of S301's orbit also highlights the importance of long-term observational campaigns in astronomy. Unlike short-term events like supernovae or planetary alignments, the study of stellar orbits around black holes demands sustained effort over decades. This is because the gravitational effects of a supermassive black hole are subtle and require precise measurements to detect. The time-lapse data from S301's orbit is a testament to the power of modern astronomy, where telescopes and computational tools work in tandem to reveal the hidden mechanics of the universe. Yet, the implications of these observations go beyond the immediate study of black holes. They contribute to a broader understanding of how gravity operates on a cosmic scale, influencing the formation and evolution of galaxies. Supermassive black holes are not isolated entities, they are deeply intertwined with their host galaxies, regulating star formation and shaping the distribution of matter. By studying how stars like S301 interact with their environment, scientists can better model these relationships, shedding light on the complex interplay between dark matter, gas dynamics, and gravitational forces. This, in turn, helps us address fundamental questions about the structure and fate of the universe. The study of S301's orbit is also a reminder of the vast unknowns that still exist in astrophysics. While we have made significant strides in understanding black holes and their effects, there are still mysteries to unravel. For example, how do supermassive black holes grow to such immense sizes? What role do they play in the early universe? And how do their gravitational influences affect the surrounding cosmos? Observations like those of S301 provide critical data to address these questions, pushing the boundaries of our knowledge. In this way, the time-lapse of S301's orbit is more than just a scientific curiosity, it is a pivotal piece of the puzzle in our quest to comprehend the universe's most enigmatic phenomena. By studying this star's journey around the black hole, we are not only gaining insights into the nature of gravity and spacetime but also deepening our understanding of the forces that shape the cosmos. The significance of these observations lies in their ability to connect the microcosm of individual stars with the macrocosm of galaxies and beyond, bridging the gap between theoretical predictions and empirical evidence. As we continue to refine our instruments and expand our observational capabilities, the study of stars like S301 will remain a cornerstone of astrophysical research, guiding us toward a more complete picture of the universe's workings. For centuries, the idea of a black hole was more myth than science. Ancient astronomers observed the night sky with wonder, but the concept of a region in space where gravity is so intense that not even light can escape was first proposed in the 18th century by Jean-Michel and Pierre-Simon Laplace. These early thinkers imagined objects so massive and dense that their gravitational pull would trap even the fastest particles. However, it wasn't until the 20th century, with Einstein's theory of general relativity, that black holes became a serious subject of study. Einstein's equations predicted that space and time could bend around massive objects, and in extreme cases, collapse into singularities surrounded by event horizons. Yet, for decades, these ideas remained theoretical, lacking observational evidence to confirm their existence. The breakthrough came in the 1970s, when astronomers began to notice something extraordinary at the center of our galaxy. A radio source named Sagittarius A*, a faint, compact region at the Milky Way's core emitted intense radio waves, suggesting something massive and dense was lurking there. But how could scientists prove it was a black hole rather than a dense star or a cluster of objects? The answer lay in watching the motion of stars orbiting this mysterious point. In the 1980s, a team led by Reinhard Genzel and Andrea Ghez began using ground-based telescopes to track the movements of stars near Sagittarius A star. Their observations revealed that these stars were moving at incredible speeds, far too fast to be explained by the gravity of a single star. This hinted at the presence of an invisible, massive object, something so dense that its gravity could bend the fabric of spacetime itself. Yet, the data was limited by the resolution of ground-based telescopes, which struggled to capture the fine details of stars so close to the galactic center. The breakthrough came in the 1990s with the advent of adaptive optics, a technology that allowed telescopes to compensate for atmospheric distortions and achieve unprecedented clarity. The European Southern Observatory's Very Large Telescope, VLT, in Chile became a key player in this quest, using adaptive optics to peer deeper into the galactic core. By the 2000s, astronomers had identified several stars, including S2, that orbited Sagittarius A* in highly elliptical paths. These stars provided the first direct evidence that the galactic center harbored a supermassive black hole. The data showed that the stars' orbits were consistent with the gravitational pull of an object with a mass millions of times that of the Sun, compressed into a region no larger than our solar system. This was a monumental confirmation of Einstein's predictions, but it also raised new questions. How did such a massive object form? What role did it play in shaping the galaxy's evolution? The answers required even more precise observations. In the 2010s, the Gaia mission and advanced spectroscopic techniques allowed scientists to measure the velocities of stars with greater accuracy. These measurements refined our understanding of the black hole's mass and helped rule out alternative explanations, such as a cluster of neutron stars or a dense stellar object. Meanwhile, the Event Horizon Telescope (EHT) project, launched in the 2010s, began capturing images of black holes across the universe. While the EHT's first major success was imaging the supermassive black hole in M87*, its work also provided insights into the dynamics of the Milky Way's central region. The EHT's observations of Sagittarius A** revealed fluctuations in the accretion disk around the black hole, further validating theoretical models of black hole behavior. Yet, the most dramatic breakthrough came in the 2020s, when long-term observations of stars like S301 provided the first time-lapse of a star orbiting the galactic black hole. These observations, spanning decades, allowed scientists to track the star's path with incredible precision. The data not only confirmed the black hole's existence but also offered a unique opportunity to test Einstein's theory of general relativity in an extreme environment. By analyzing the star's orbit, researchers could measure how spacetime curves around the black hole and whether the predictions of general relativity hold under such intense gravitational forces. This work built on decades of foundational research, from the early radio astronomy discoveries to the development of adaptive optics and space-based observatories. Each step in this journey required overcoming technological limitations, refining observational techniques, and pushing the boundaries of what we could see in the universe. The time-lapse of S301 is not just a snapshot of a star's motion, it is a testament to humanity's relentless pursuit of knowledge. It connects the earliest speculations about black holes to the cutting-edge science of today, showing how each discovery builds on the last. As we continue to study the galactic center, we are not only unraveling the mysteries of black holes but also gaining insights into the fundamental nature of gravity, spacetime, and the forces that shape the cosmos. The story of S301 is part of a larger narrative, one that spans centuries of scientific inquiry and the ingenuity of astronomers who dared to look beyond the stars. The time-lapse of star S301 orbiting the supermassive black hole at the Milky Way center has become one of the most compelling tests of Einstein's general relativity. Yet even as scientists marvel at the precision of these observations, they remain humbled by the profound mysteries they reveal. The data collected over years of monitoring S301's motion around Sagittarius A*, the black hole at our galaxy's heart, has confirmed many predictions about how gravity warps spacetime. But it has also raised questions that challenge our understanding of black holes, stars, and the very fabric of the universe. For instance, how do we know the measurements of S30, the star's orbit, are accurate enough to rule out alternative theories of gravity? What aspects of the black hole's behavior might still elude our models? And what does the star's peculiar journey tell us about the extreme conditions near a black hole's event horizon? These are not just academic puzzles, they are fundamental questions about the nature of reality itself. The observations of S301 are a window into the cosmos, but they also remind us that even the most advanced tools of modern science cannot yet see everything. Let's explore what remains unresolved, what debates persist, and why these mysteries continue to drive scientific inquiry. One of the most pressing uncertainties lies in the precision of the measurements themselves. While the time-lapse data has been hailed as a triumph of observational astronomy, the process of tracking S301's position over time is fraught with complexities. The star is located thousands of light-years away, and its motion is minuscule on human timescales. To detect such subtle changes, astronomers rely on instruments like the Very Large Telescope and the Keck Observatory, which capture images with incredible resolution. Yet even with these tools, there are limits to how precisely we can measure the star's trajectory. For example, the exact shape of S301's orbit, whether it is perfectly elliptical or slightly perturbed by unknown forces, remains a topic of debate. Some scientists argue that the observed deviations from a simple Keplerian orbit could hint at the influence of dark matter or other exotic phenomena. Others caution that such deviations might simply be the result of measurement uncertainties or the complex interplay of gravitational forces in the galactic center. These uncertainties underscore a broader challenge: how do we distinguish between real physical effects and the limitations of our observational techniques? The answer could shape our understanding of both the black hole and the stars that orbit it. Another layer of mystery lies in the black hole's properties themselves. While Sagittarius A* is well established as a supermassive black hole with a mass of about 4 million solar masses, there are still questions about its exact characteristics. For instance, the spin of the black hole, a key parameter in general relativity, is difficult to measure directly. The time-lapse of S301's orbit provides indirect clues about the black hole's spin, but these clues are not definitive. A rapidly spinning black hole would exert stronger tidal forces on nearby objects, potentially altering the star's trajectory in ways that are hard to quantify. Yet the data so far suggests that the black hole's spin is relatively moderate, which raises new questions. If the black hole were spinning faster, would S301's motion look different? And if the spin is indeed low, what does that imply about the history of the black hole's growth? These are not just theoretical musings, they are critical for understanding how supermassive black holes evolve over cosmic timescales. Moreover, the environment around Sagittarius A* is anything but simple. The galactic center is a dynamic region where stars, gas, and magnetic fields interact in complex ways. While the time-lapse of S301 focuses on the star's orbit, it also highlights the challenges of isolating the black hole's gravitational effects from other influences. For example, the star's motion could be affected by the gravitational pull of nearby stars or the drag of interstellar gas. Scientists have attempted to account for these factors, but the interplay of forces in such a crowded region remains poorly understood. This complexity means that even a seemingly straightforward observation like S301's orbit could be influenced by a multitude of variables, some of which may still be beyond our current models. The implications of these uncertainties extend beyond the immediate study of S301. They touch on broader questions about the nature of gravity and the validity of Einstein's theory in extreme conditions. General relativity has withstood countless tests, from the bending of light around the sun to the precise timing of pulsars. Yet the extreme environment near a black hole, where spacetime is stretched to its limits, offers a unique laboratory for probing the theory's boundaries. The time-lapse of S301's orbit has provided some of the strongest evidence yet for general relativity's predictions, but it has also revealed gaps in our understanding. For instance, the star's motion suggests that spacetime is curved in ways that align with Einstein's equations, but there are still questions about how precisely these effects manifest. Could there be subtle deviations that hint at new physics? Some scientists have proposed that alternative theories of gravity, such as those involving extra dimensions or modified gravitational forces, might explain certain aspects of the observations. While these ideas remain speculative, they highlight the fact that even the most successful theories can be challenged by new data. The debate over the validity of general relativity in extreme conditions is far from settled, and the study of S301's orbit continues to play a role in this ongoing conversation. Beyond the immediate scientific questions, the observations of S301 also raise philosophical and existential inquiries. What does it mean to observe a star orbiting a black hole in such detail? How does this experience shape our perception of the universe's vastness and complexity? For many scientists, the time-lapse of S301 is a humbling reminder of how much we still do not know. Despite the incredible technological advances that have made such observations possible, the galaxy's center remains a region of profound mystery. The black hole's event horizon, the point of no return, is still a place where our understanding of physics breaks down. While we can model the behavior of stars and gas in the vicinity, the true nature of what lies beyond the event horizon remains elusive. This is not just a technical challenge, it is a testament to the limits of human knowledge. Yet it is also a source of inspiration. The study of S301's orbit is a reminder that science is a process of continual discovery, where each answer leads to new questions. The time-lapse of this star is not just a snapshot of its motion, it is a glimpse into the dynamic, ever-evolving universe. As scientists continue to refine their measurements and models, they are not only deepening their understanding of black holes and stars but also pushing the boundaries of what is possible in observational astronomy. The mysteries surrounding S301's orbit are far from solved, but they are precisely what makes this research so compelling. They challenge us to think critically, to question our assumptions, and to embrace the unknown. In the end, the study of S301 is more than a technical achievement, it is a celebration of human curiosity and the relentless pursuit of knowledge. As we look to the future, the unresolved questions about this star's journey will undoubtedly shape the next generation of discoveries, reminding us that even in the most extreme environments, there is always more to learn. As we look ahead, the study of S301 and its journey around Sagittarius A* is far from complete. The next few decades could bring groundbreaking revelations, thanks to a combination of cutting-edge technology, ambitious space missions, and refined observational techniques. Already, astronomers are planning ways to extend our understanding of this system, not just to confirm what we've already observed, but to test the limits of our current theories about gravity, spacetime, and the extreme environments around black holes. Let's explore what's coming next in this scientific quest. One of the most exciting frontiers lies in the next generation of space telescopes. The James Webb Space Telescope, already revolutionizing our view of the universe, has already begun capturing high-resolution data of the galactic center. But its successor, the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, promises even greater capabilities. With its wide field of view and advanced coronagraphs, the Roman telescope will be able to block out the light from Sagittarius A* itself, allowing astronomers to study the stars orbiting it in unprecedented detail. This could reveal subtle variations in S301's motion that might hint at new physics or refine our understanding of how black holes influence their surroundings. Additionally, the upcoming Nancy Grace Roman Space Telescope will be equipped with instruments capable of detecting minute shifts in the star's position over time, potentially uncovering effects like frame dragging, where spacetime itself is twisted by the black hole's immense gravity. These observations could provide direct evidence of Einstein's general relativity in its most extreme form. Meanwhile, ground-based observatories are also advancing. The Extremely Large Telescope, ELT, currently under construction in Chile, will be the largest optical telescope ever built. With its 39-meter primary mirror, the ELT will have the power to resolve details in the galactic center that are currently beyond our reach. Its adaptive optics systems, which use deformable mirrors to counteract atmospheric distortion, will allow astronomers to track S301's orbit with extraordinary precision. This could help confirm whether the star's motion aligns perfectly with predictions based on general relativity or if there are deviations that suggest something more complex is at play. Similarly, the upcoming Giant Magellan Telescope, GMT, in Arizona and the European Extremely Large Telescope, ELT, in Spain will contribute to this effort, offering new ways to study the dynamics of stars near the galactic center. These observatories are not just about improving resolution, they're about pushing the boundaries of what we can observe in regions of the universe that are otherwise obscured by interstellar dust and gas. Beyond Earth-based and space-based telescopes, the field of gravitational wave astronomy is also poised to play a role. While S301 itself is too massive to emit detectable gravitational waves, its interactions with the black hole or other nearby objects could, in theory, produce ripples in spacetime. Instruments like LIGO and Virgo have already detected gravitational waves from merging black holes and neutron stars, but their sensitivity is limited to certain frequencies. Future observatories, such as the Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will be able to detect lower-frequency gravitational waves, potentially revealing new insights into the dynamics of the galactic center. If S301's orbit is perturbed by unseen masses or if the black hole itself experiences sudden changes in its spin or accretion disk, these disturbances could generate detectable gravitational waves. While this scenario is speculative, the development of LISA represents a major leap in our ability to probe the hidden mechanics of the universe. Another key area of focus is the refinement of our models for how stars interact with supermassive black holes. Current simulations rely on our understanding of general relativity, but there are still gaps in how we account for factors like the black hole's spin, the distribution of dark matter in the galactic center, or the effects of quantum gravity at extreme scales. Future missions like the European Space Agency's Plato, Planetary Transits and Oscillations of Stars, and NASA's Habitable Worlds Observatory could provide data on other stars in the galactic center, helping to build a more comprehensive picture of the environment around Sagittarius A star. By comparing the orbits of multiple stars, including S301, scientists can test whether the black hole's gravity behaves as predicted or if there are anomalies that suggest the presence of unknown phenomena. For example, if S301's orbit deviates from theoretical predictions in ways that cannot be explained by existing models, it could hint at new physics such as modifications to general relativity or the existence of dark matter clumps that exert an unseen gravitational pull. The study of S301 also has implications for our understanding of stellar evolution in extreme environments. Stars orbiting supermassive black holes are subjected to intense gravitational forces, extreme tidal stresses, and high-energy radiation. Observing how S301 behaves over time could shed light on how such stars survive and evolve in these conditions. For instance, if the star's brightness or spectral characteristics change over its orbit, it might indicate interactions with the black hole's accretion disk or the presence of a companion star. Future instruments equipped with advanced spectroscopy capabilities, such as the James Webb Space Telescope's near-infrared spectrograph, NIR-SPEC, could analyze these changes in detail. By studying the star's light across different wavelengths, astronomers might uncover clues about its composition, temperature, and even the presence of elements forged in the extreme conditions near the black hole. Such findings could help us understand how stars in the galactic center are affected by their environment and whether they can serve as natural laboratories for testing astrophysical theories. In addition to refining our models and expanding our observational tools, future research may also challenge our assumptions about the galactic center itself. The current understanding of Sagittarius A* is based on observations of its accretion disk, magnetic fields, and the motion of nearby stars. However, there are still uncertainties about its exact mass, spin, and the nature of its event horizon. If S301's orbit reveals unexpected patterns such as a slight wobble that cannot be explained by known factors, it could indicate that the black hole's properties are more complex than previously thought. For example, if the star's motion suggests the presence of a secondary object orbiting the black hole, it could provide evidence for a binary system that has eluded detection. Alternatively, if the star's trajectory deviates in ways that cannot be accounted for by existing theories, it might hint at the need for new frameworks to describe gravity in extreme conditions. These possibilities underscore the importance of continued observation and the development of more sensitive instruments. Another exciting direction is the potential for citizen science and collaborative efforts to contribute to the study of S301. As data from telescopes like the Event Horizon Telescope, EHT, and the upcoming Next Generation Very Large Array, INGVLA, becomes more accessible, amateur astronomers and enthusiasts may play a role in analyzing patterns or anomalies in the data. The EHT's recent images of the black hole's shadow have already sparked public interest, and future observations of the galactic center could similarly engage a broader audience. By involving the public in the analysis of time-lapse data or the classification of stellar behavior, scientists can harness collective intelligence to uncover new insights. This democratization of science not only enhances the reach of astronomical discoveries but also fosters a deeper connection between the public and the mysteries of the universe. Finally, the study of S301 is part of a larger effort to understand the role of supermassive black holes in shaping galaxies. These cosmic giants are thought to influence the formation and evolution of their host galaxies through mechanisms like feedback from accretion disks and relativistic jets. By studying how stars like S301 interact with Sagittarius A*, we can gain a better understanding of these processes. For example, if S301's orbit is affected by the black hole's jet activity or magnetic fields, it could provide direct evidence of how such forces impact the surrounding environment. Future missions focused on mapping the galactic center's magnetic fields, such as the Square Kilometre Array (SKA) radio telescope, could complement these observations by revealing how energy and particles are transported across vast scales. These insights would not only deepen our knowledge of the galactic center but also inform our understanding of black holes in other galaxies. In conclusion, the journey of S301 around Sagittarius A* is far from over. As technology advances and new observatories come online, we are poised to unlock even more secrets about this dynamic system. Whether through the precision of space telescopes, the power of gravitational wave detection, or the collective efforts of the global scientific community, the next chapter in this story promises to be as thrilling as the one we've already witnessed. The study of S301 is not just about tracking a single star, it's about pushing the boundaries of our knowledge and exploring the fundamental forces that govern the universe. And as we continue to peer into the heart of our galaxy, we may yet discover that the cosmos has more surprises in store for us. As we wrap up this deep dive, 3 ideas stand out. First, the star S301's orbit around Sagittarius A*, the supermassive black hole at our galaxy's center, reveals how gravity bends time and space in extreme conditions. By tracking this star's journey over years, astronomers captured a time-lapse that's more than just a visual spectacle, it's a living experiment in Einstein's theory of general relativity.
Second, the observations highlight the power of modern astronomy.
Instruments like the Very Large Telescope Interferometer (VLTI) allowed scientists to peer into the galaxy's heart, resolving details so fine they can measure how light from S301 is stretched by the black hole's gravity.
Finally, this work isn't just about a single star, it's a window into the universe's most extreme environments.
By studying S301's dance around a black hole, we test the limits of our understanding of spacetime, gravity, and the forces that shape galaxies. These findings remind us that the cosmos is still full of mysteries waiting to be unraveled. If you enjoyed this journey through the heart of our galaxy, hit that subscribe button for more deep dives into the wonders of space. And if you have questions or theories about what S301's future might hold, drop them in the comments. We're always curious to hear your perspective.
Until next time, keep looking up.